Welcome to qnawire.
Here we have a glider compressed against a spring and released. Now this launcher has a force constant K and is compressed by a distance of x, and the glider is released from rest. Now let's see what the speed is going to be based on the conservation of energy equations. So we know that all mechanical energy that we start off with has to equal all mechanical energy that we end up with based on the conservation of energy law. So let's write down all of the energy types that we could possibly have. We have kinetic energy, we have gravitational potential energy, and we have the spring elastic potential energy. And this is all in our initial case. And this is always going to equal to our final case. So 1/2 mv final squared plus mgh final plus 1/2 k x squared final. Now, in our first case, we are at rest, so we do not have kinetic energy. We're not falling under the effects of gravity, so there is no gravitational potential energy. We are, however, using a spring and therefore elastic energy, so the 1/2 kx squared will remain. After it is released, it does have kinetic energy. There is still no potential energy, and it's lost all of its elastic potential energy. So what we end up with is the equation 1/2 kx squared is equal to 1/2 mv squared. And now we can rearrange that to figure out what v is equal to. We can get rid of these halves right here, divide both sides by m, and we end up with v squared equal to kx squared divided by m. And then by taking the square root of both sides, v is equal to k over m to the power of 1/2 multiplied by x. Perfect. So let's see what the impulse is going to be based on the velocity we just found. Impulse is the change in momentum, right? So I is equal to mass multiplied by your change in v. Now we know our initial case is no motion, so our final velocity is the only velocity that matters, which in this case was k over m to the power of 1/2 times by x. Now we have two factors of m in here, so what we can do is we can neaten this up a little bit and say we have x multiplied by km to the power of 1/2. Now finally, the amount of work done is based on the energy. So in this case here, the mass would not have an effect. If we had a mass of twice the size, the amount of work done would not change because the velocity would decrease as an effect of the larger mass. So with regards to mass, there is no difference. Mass here is not a factor.